going to go ahead and get started. Thank you, everyone, for coming. My name is Laura Gritt, and I am a Principal Technical Program Manager at Amazon. I've been at Amazon for 5 years, and during that time, I have worked for the Amazon retail business. Now, when I say Amazon retail, I mean everything that's not AWS. There's a common misconception that AWS was created specifically for Amazon retail, but nothing can be further from the truth. We operate as completely separate businesses in Amazon. We report into different senior vice presidents, we sit in different buildings, and we also operate independently. Like you, Amazon Retail is another user of AWS. We work with account managers, technical account managers, and solutions architects as we design our solutions and approaches to AWS and to the cloud. Today I've been invited here to talk to you about how Amazon Retail is using AWS to power our retail business. Now, I'm presenting this talk from the perspective of Amazon Retail. So when I say Amazon, I mean the retail side of the business. When I mean AWS, I'll specifically say AWS. Over 2.5 years ago, I took over an initiative called Moving Amazon to AWS, or MOZ, as we refer to it internally. While Amazon has been using AWS services ever since S3 launched, we wanted to have a program that looked across our company to see if we were approaching our migration at the right pace, and also if we were taking big steps towards AWS as opposed to incremental ones. We wanted to make sure that we were creating the right culture with our engineers so that they were looking towards AWS first for their service solutions. Here's the top reasons why Amazon Retail is looking at AWS and why we're migrating to AWS. The first is to enable our engineers to go faster. By using AWS services, we don't have to start everything from scratch, and can instead spend time working on the things we want to spend time on, which is building out differential features for our customers. Things like putting servers into racks is not something that we want to spend our time doing, and we happily let AWS do that for us. The next reason that we look at AWS is to decrease our costs of our business. Doing things like right-sizing our fleets and by dynamically scaling our fleets, we've been able to save costs as we've migrated to AWS. Last, and equally important, is we want to influence the AWS roadmap. Whenever our engineers find features or services that they feel that AWS should be providing, we make sure to submit those requests. Now, just because Amazon Retail submits a request to AWS, it does not get to the top of the priority queue. There's no direct line for Amazon Retail to jump above everyone else. Instead, AWS includes the Amazon Retail requests with all of the other requests that they're getting from their users to figure out what makes sense for their business and what their customers really need. While we focus on building out new services directly on AWS for Amazon Retail, we have a lot of services that predate AWS. And in fact, we found that it's different to migrate existing services to AWS than it is to build directly new services on AWS. So today I'm going to talk to you about how Amazon Retail approaches migrating services to AWS, and also come back to point 1 here about how using AWS has enabled our engineers to go faster and what that has meant for us as an enterprise. As I mentioned, since S3 was launched, we have been migrating services to AWS. In fact, anytime AWS has a new service launch, there are multiple teams in retail that are signed up for their beta release. In fact, for Amazon Redshift, as Andy Jassy mentioned earlier, our Amazon Data Warehouse team is signed up and has been working with them on the product. However, the biggest migration that we did, and one that occurred early in the Move to AWS program at Amazon, was the migration of the Amazon.com web server fleet. And as the head of the program, that's the one that I get asked the most about. So I want to dig into that a little bit. So why did we start looking at migrating the Amazon.com web server fleet to AWS in the first place? This is a typical weekly graph of Amazon traffic. You see that we have peaks during the day and troughs at night. Also, we have pretty consistent traffic between the different days. If you manage a website, you might be very familiar with this type of traffic trend. We require capacity that aligns with this graph. During the day, we require thousands of servers to support the traffic coming into Amazon.com. And at night, we don't need as many when we don't have as many customers working on the site. I'm going to be referring in this talk to something called a fleet. A fleet is what we call a collection of servers or instances required to host an application or service. So we don't just keep capacity in the Amazon.com fleet at the blue line. Instead, we keep capacity at this red line, which represents the max capacity we require for our traffic, plus a 15% buffer in case we have any unexpected traffic demands. We got pretty good as a company at figuring out where to set this red line, unless there were any unannounced sales events or other external factors that caused our traffic to spike. The problem is there's a lot of space between that red line and the blue line on the graph. And all of that represents the capacity that we own, but don't actually need for our service. So how much is going to waste? The blue area here represents the capacity that we actually need to host the Amazon.com website, and the red represents the capacity that we own, but don't actually use during the course of the week. You can see that on an average week, we were wasting about 40% of our capacity for the web server fleet. However, the problem is actually worse than that. You see, we don't just have a daily cycle for the website. Instead, we have an annual traffic cycle that follows the normal retail cycle. So this shows the traffic over the course of November. Our traffic progressively goes up as we get closer and closer to the peak time of the year. And in November, you see it gradually ramps up until we hit Black Friday and Cyber Monday. We have capacity that comes in terms of a step function. So for our data centers, we don't just purchase a single server at a time to scale linearly. Instead, we purchase servers on the order of a rack. And so what that means is we have a step function of capacity coming in, and at some point in time, we're actually going to run out of space in our data center. When we run out of space in our data center, in order to add that next server and that next rack that we need, we're going to need to build an entire new data center in order to incrementally increase the amount of servers that we have for our website. That's going to require serious lead time and require millions of dollars to do. Now, even that doesn't show the extent of our wasted capacity problem. For Q4, we want to make sure that we have capacity in place well before peak. We don't want our servers coming in just right before, depending on the amount of time that it takes to procure and provision our hosts in our data center. So in actuality, this is what our held capacity looked like on an average November, where we got all of our capacity in place well ahead of when we actually needed it towards the end of the month. And of course, after our peak, while our traffic exits the year higher than we come in as we gain new customers through the holiday season, we still have excess capacity that we purchased for that peak season that we now don't need come January or February. So how much was going to waste in an average November? You can see here about 3/4 of our capacity we didn't actually require throughout the course of an average November. Now, this is not consistent with Amazon's retail goal of providing our customers the lowest possible prices on the items that we sell. One of the main benefits that people talk about for cloud computing is the ability to dynamically scale capacity up and down when you actually need it. The idea is when you don't need capacity, you release it back to the cloud and you don't pay for it during that time. And then when you need capacity again, you simply get it back. And from this data, the web server fleet should be the poster child for this type of dynamic scale story. So from this data, the problem's pretty obvious. We want to move the Amazon.com web server fleet to handle our wasted capacity. Now, one more thing. There's also a common misconception that all of this red area is actually what AWS sold to customers. That's not true. This was sitting idle in the Amazon.com data center, just sitting there waiting to be used. So we started looking at migrating the web server fleet, but how are we going to do this? We started looking at what EC2 had to offer and discovered it wasn't going to be as straightforward as just simply putting the web server fleet on EC2. So when we started looking, we're like, well, we definitely want the web server fleet running on AWS and EC2. But the web server fleet calls back to a lot of dependencies that were still in the Amazon retail data center. In addition, there were backend databases, and also over the years, we built a lot of tools to help our engineers manage our fleets. Were we going to need to migrate the web server fleet, all of its dependencies, all the backend databases, and all of our tools at the same time? While the goal of the Move to AWS program at Amazon is to move everything to AWS, that would be a lot to tackle at once. And we really wanted to have a big win with migrating the web server fleet and migrate the rest as it was appropriate. So we started talking to EC2 and found out they had heard similar concerns from other enterprises and had started working on a set of products that would enable enterprises to extend their data center into AWS. And when we heard about this, we volunteered to be early adopters of the products. So the technical solution to migrating the web server fleet was to utilize the Virtual Private Cloud product and the AWS Direct Connect products. We used the Virtual Private Cloud to carve out a section of AWS and have it be for Amazon. It also allows us to assign our own IP addresses to those EC2 instances. We then use the AWS Direct Connect product to create a dedicated connection between the Amazon retail data center and our VPCs in AWS. What this really meant for us is once we had EC2 instances connected back to the Amazon retail data center, we could focus on the web server fleet migration in isolation and then start looking at the other parts of our architecture. As we predicted, so the web server fleet had been finely tuned over the course of many years to run on a specific type of physical server. And anytime we upgraded to a new version of the physical server, or anytime we migrated to a new version of Linux, there were always problems with the web server fleet. And the team that managed the fleet would have to spend a lot of time figuring out how to get that web server fleet running on that new type of hardware. So as we approached the migration, just getting the Virtual Private Cloud and AWS Direct Connect products in place was not the end of the migration. We knew going from our specific physical server type to EC2 instances was going to require some work. And as we predicted when we started testing, we found that there were going to be different performance characteristics, and we needed to invest the time in making the web server fleet run high performantly on EC2. And so a big part of the web server migration was actually doing a deep dive in our own performance in terms of CPU, memory, I/O, and doing things like reducing our memory footprint so that we could run the web server fleet at equal performance on EC2 as we had before. And I'm happy to say that after a lot of testing and some changes to our software, we were able to get the web server fleet running on EC2. This date, November 10th, 2010, is the day we turned off the last physical web server in the Amazon.com data center for the web server fleet. Since this day, every web page to the Amazon.com website has been rendered on a fleet of EC2 machines. Now, look at this date. This happened just a little bit before Black Friday in 2010. Now, people might think we're a little crazy to make that big of an architectural change right before Q4, and believe me, we got a lot of questions inside Amazon as well. However, notice I said that November 10th was the day we turned off the last physical web server. We didn't just do one big flip over to EC2 and hoped everything worked. Throughout the course of the previous year, we had tested, incrementally migrated, and verified that we were good to go on EC2 and only fully migrated once we were 100% confident that we could run at high performance on EC2 and EC2 could handle our scale for Q4 that year. And I'm happy to say that in Q4 2010, we had excellent performance, and our availability was of that or higher than what we had before when we ran in our own data centers. In fact, we're going through our third peak season now on EC2, and our availability and performance has been fantastic. So going back, did we solve the problem we had in the first place of having underutilized capacity for the Amazon.com web server fleet? And the answer is yes. This dotted line represents our held capacity now that we're in EC2. We still retain our 15% buffer to quickly be able to handle unexpected traffic demand, but through releasing capacity when we don't need it, we've been able to save over 25% of our cost with going to EC2. As a matter of fact, we didn't just solve some cost problems and capacity held problems. We also helped reduce some operational load for the developers that were managing the web server fleet. And I want to dig into that a little bit more because that's been an important part of our migration story from a program perspective. So let's go back to our held capacity before we went to EC2. We once again have our flat line at about 15% above what our max is going to be for the week. Let's say Tuesday night we have a multi-rack outage. Now, even though we paid for and we own the capacity, we now have less available capacity than we had before and less than what we need for the rest of the week. We handle this as you'd expect. We get a lot of people on the phone on Tuesday night and figure out what happened to the racks, and eventually, with a lot of heroics, get the racks back up, and now we're good to go for the rest of the week. However, come Friday, we discovered that the GameBox 7000 has launched, and we weren't told ahead of time. Now we have traffic that's going higher than what we predicted our max traffic was going to be for the rest of the week. So once again, we get a bunch of people on the phone and figure out how to scramble to find extra capacity from inside our data centers to put inside the web server fleet. And with heroics, we once again get extra capacity, and we're good to go. However, now we have even more capacity from when the sale ends than what we actually predict we need for the next week. And we need to figure out what we're going to do with that extra capacity. Now that we're on EC2, the process is completely different. And in fact, we don't just use EC2 for the web server fleet, we use EC2 with auto-scaling. Auto-scaling is a feature of EC2 that detects if a host goes down and does automatic replacement of it, as well as dynamic scaling of fleets. So let's step through the same series of events and see what it looks like now that we're on EC2. First, there's a multi-rack outage on Tuesday night. There's a blip in our available capacity, but auto-scaling detects that our instances went down and immediately launches new instances to replace them. The main thing here is no one in Amazon retail has to get on a call to handle this. We automatically recover through auto-scaling. Now, I'm assuming someone in EC2 had to handle the fact that we had a multi-rack outage, but not our problem. We got our replaced instances, and everyone in Amazon retail can go through without getting paged. Now, we once again have our sale on Friday. And once again, it's not a fire drill. We simply see through auto-scaling that our CPU is running hotter than expected, and we add more EC2 instances to the fleet. And of course, compared to before, once the sale is done, we can return the extra capacity we got back to EC2, and we don't have to pay for it anymore. And in fact, this is how we handle our big launches now, such as the Kindle Fire launch from earlier this year. Now that we're on EC2, if we mispredict our capacity needs, it's not a big deal anymore. We simply go and add more machines from EC2. Moving the web server fleet not only got the business excited about the cost savings and our ability to scale linearly, but also got developers excited about the operational load decrease that they had to burn. One benefits of this migration were shown to the rest of the company. It actually jump-started a wave of migrations to EC2 from inside Amazon retail. And we found from a program perspective, this has been important, to find early migrations that benefit both the business and the developers, because then they both are working together to figure out how to move their services to AWS. At Amazon, we don't force anyone to migrate. Instead, we lure teams to migrate themselves to AWS with the benefits that they're going to gain through the migration. When you're considering migrating your enterprise to AWS, it's also important to consider your application stack. Look at the different services that you have at your company and determine how complex that migration is going to be and what you're going to get in return from that migration. Also important, especially for early migrations, is to look at who owns the service you're considering migrating. Determine that team's level of ownership, their technical expertise, and their motivations and their excitement about getting that service running on AWS. You may choose to not migrate the simplest service that you have in your company, but instead one that will create a cultural change in the company and force more migrations automatically to AWS. In the case of the web server fleet, They had very spiky traffic demands, which made them an ideal use case for EC2. However, it's a really big fleet. It's thousands of machines, and it's also a major revenue source for Amazon. So if the migration didn't go well, that could be a big risk to our company. However, it's stateless in that we don't retain state on the Amazon retail fleet, and so that made it a little bit easier of a service to migrate than some of our more complex services we have in our company. Also, the team had good technical ownership and also was incredibly motivated to get the web server fleet to EC2. In the end, we chose to migrate one of our big services in order to make a point that if the web server fleet could migrate, other services with similar characteristics would be able to migrate as well, and that's exactly what happened in Amazon. So the web server fleet was stateless, as I mentioned, but what about services that retain data? There's probably no piece of our infrastructure that's proven more problematic over the years than our databases. We constantly struggled to get our relational databases to scale at the pace of our business. So let's take a look at a service that migrated to handle their database scaling problem. One of the promises that Amazon makes to our customers is that you will always be able to see the past orders that you placed on Amazon. Here you can see a screenshot of my order history page. And circled in right, you can click on any of the years that I have made a purchase on Amazon, and I can see what orders I have made. As you might imagine, in the course of our history, our customers have placed billions of orders. And a few years ago, we made an interesting discovery. Most discussions around database scaling involves the transactions per second that the database can handle. However, when we were looking at our infrastructure costs, we stumbled upon the fact that for us, there was an equally important, if not more important factor in our ability to scale, and that was the cumulative amount of data stored by the database. And if you think about it, it makes sense. The more data you get into your database, the more memory pressure you're going to be putting on that hardware. And by reducing the cumulative amount of data that you have, the more requests can be handled in memory as opposed to going to disk. So here's a high-level architecture overview of our ordering service. It's a pretty straightforward service-oriented architecture. The web servers talk to the ordering service, which in turn talks to the ordering database. Below, you can see the two most common ways that people scale databases. Pattern one, you simply buy bigger and bigger databases to handle the increased amount of data and transactions you need for your database. In the second, you shard your data across multiple databases. Pattern one gets more expensive as you move to more and more exotic types of hardware. And eventually, you're going to hit a wall where there isn't hardware that's big enough to handle the size of your database. In the second pattern, it becomes much more complex in the case of failures, replication, and handling inter-server communication. Ultimately, neither of these patterns make us happy. So the problems are pretty straightforward. First, we found that cumulative amount of data, not just transactions per second, were impacting our ability to scale our databases. Second, we didn't really like either of these approaches. They each have its own pitfalls. Third, the most expensive hardwares we have in the Amazon retail data center are our database hosts. Our DBAs require us to get high-end, expensive components for them to host our applications. So to the extent that we can reduce the number of database boxes we have in the Amazon.com retail data center, the lower our costs are going to be for our business. The solution we came up with was to create a tiered storage architecture for the ordering service, utilizing AWS data stores, specifically in this case S3. The solution takes advantage of the fact there's actually two types of data being stored in the ordering database. The first are the orders that are still changing pretty rapidly. Those where customers are checking to see what their delivery dates are, or those where customers are going to return orders that they determine they no longer need. The second type of data are the orders that are now closed, those that aren't changing and are immutable. The architecture looks like this. What the ordering service does is they denormalize the older orders from the relational database and push them to S3 encrypted. They then keep a pointer from the relational database to S3 to find the older orders. What made this possible is that the ordering service made changes to their application to allow them to read from two different types of data stores, the relational data store and the S3 data store. The team's early in their migration, but so far they've moved more than 670 million orders to their S3 encrypted repository. That's a lot less database hosts that we need for hosting the ordering service now than we did before. By removing all of this cold data, it's actually reduced the amount of money that we need to spend on the ordering fleet. And although S3 is slightly slower than pulling directly from a relational database, we have discovered it doesn't impact our customers. Our customers intuitively assume that it's going to take a little bit longer to pull orders from 2002 than it does to pull an order that was placed yesterday. Finally, moving the older orders from the relational database to S3 is really the ordering service first phase on their migration to AWS. By reducing the size of their relational database and by changing their code to be able to pull from multiple types of data sources, they are now in a position to start looking at where they're going to migrate the data from the relational database into something like RDS or DynamoDB. So I've gone through 2 examples of services that have done migrations to AWS. And here in general is what we've learned from a program perspective about migrating our enterprise to AWS. While there's a goal of having everything migrate, not everything in your company is going to migrate at the same time. For the web server fleet, getting the virtual private cloud and AWS Direct Connect products in place allowed us to do incremental migrations of our architecture to AWS. In the case of the ordering service, they were able to focus on part of their system that was causing them operational pain without having to figure out what to do with all of their different types of data. It's important to combine migrations with architectural initiatives and choose good early migration targets for your company with strong technical owners, and ones that are going to make a cultural change by setting an example of what it means to move to AWS. In fact, not everything in your company is going to migrate to AWS. For example, don't invest in migrating services that are on a path to deprecation directly to AWS. Instead, focus on building out the replacement of that service directly on AWS. In the case of the ordering service, while I showed it as a pretty simple box a couple slides ago, it's actually a very complex set of interlocking services. And that team's in the process of deprecating that service and replacing it with a new ordering service. How they're approaching their migration is they first did the older order data and put those into S3. And they're working on switching out the different parts of their application and directly building the parts they're switching out onto AWS. By the time they're done with the replacement, they'll be 100% on AWS and then be able to deprecate the older service. Also, don't expect migrations to require no changes to your applications. The web server fleet was not lift and shift, even once we had VPC in place. We still had to make changes to change from different types of hardware profiles. In the case of the ordering service, they had to make changes to their application to read from a different type of data store than a relational database. You may have to make changes in order to take full advantage of AWS services and the cloud in general. So now I want to go back to one of the key reasons that Amazon retail business is migrating to AWS, and that's enabling our engineers to move faster. We want to get the most out of our developers, and we found that they're able to innovate the best when there's not a lot of red tape getting in their way. In fact, Amazon's culture is very focused on enabling our developers. This is a quote from Jeff Bezos about the importance of providing self-service platforms to enable developer innovation. In it, he says, even well-meaning gatekeepers slow innovation. It's important for us to not get in the way of our engineers and to allow them to be creative in their solutions, and AWS has allowed us to do this. It's important as you move your enterprise that you don't dictate a single approach to how services are going to integrate or move to AWS. One way you can set an artificial gatekeeper is to tell your developers there's only one way to do things. And from the different ways that our developers have found to integrate Amazon retail with AWS, there's lots of different ways that you can approach it depending on the type of service you have. So going back to the architecture for the web server fleet migration, the VPC and Direct Connect products was really critical for the web server fleet to migrate while keeping its dependencies in the Amazon retail data center, and lots of our services have migrated using this exact same approach. However, that's not the only way that we've integrated Amazon retail with AWS. Another way that's very common at Amazon is to utilize AWS data stores. What happens is teams push data encrypted to AWS data stores and then use other AWS services to act on that data. After that data is changed or analyzed, they then push it back to an AWS data store where it's then read from Amazon Retail. And that's exactly the case of our A/B test analysis service. In Amazon, we run experiments every day on the website to determine what features our customers like best. The teams that are running the experiments then get the results of the analysis and determine what features are going to be permanent fixtures on the Amazon.com site. So what the A/B test analysis service does is throughout the day, it pushes the data from the experiments encrypted to S3. At the end of the day, it queues all of the different experiments that were run in Amazon's Simple Queue service, and then does an analysis of that data using Elastic MapReduce. Once that analysis is complete, the data is pushed back to S3, where it's then made available for the teams to analyze and look at the results of the experiments. For those of you who are not familiar with MapReduce, it's a way of expressing data, processing problems in small steps that make them very easy to parallelize across multiple machines. And data such as the test analysis data is really useful for MapReduce because it can be very parallelizable. In fact, Amazon retail teams are adopting Elastic MapReduce at a very fast pace. And they're doing so because they're finding more and more ways that they can analyze big data using MapReduce algorithms, as well as they love the fact that they don't have to host their cluster when they use Elastic MapReduce. They can simply turn off the machines to reduce costs when they're not running an analysis. And if they have a lot more data than they expected or need to get something done faster, they can simply add more EC2 machines very quickly into their Elastic MapReduce cluster to get the processing done faster. From a business perspective, AWS allows us to take more risks on projects than we could before. Unlike when we're in our own data centers, when you have a project, you might have to purchase specialty hardware that really is only useful for that project. And if that project isn't successful, you now have that hardware laying around unused until you can find another project to use that hardware. With AWS, if you have a project that doesn't succeed, you just simply release the resources back to AWS and you're not paying for it anymore. You don't have that potential long-term impact of a service not succeeding. However, if a service is successful, you can then double down on it as a business and potentially invest more in ideas that your developers have that are going to be game changers for your business. In a way, from a business perspective, you can look at AWS as a giant undo button where you don't have to pay long-term costs if something doesn't work out. I'm going to walk through an example of this at Amazon. We used to have a legacy internal video service for Amazon employees. It was really only used to host all-hands videos. And in order to get a video posted, you had to send lots of different emails to people. And in fact, once the videos got uploaded, our employees couldn't really search for where the videos were, and so the service was hardly ever used. At the same time, we had a lot of interesting talks happening at Amazon, given by different people in our business and our engineers. And if you were in another meeting at the time of the talk, or if you worked in one of our international sites, you never got to see the interesting information that was being shared. So a couple developers pitched an idea to their VP to create an internal video service for Amazon employees. He gave them a week. Worst case, it was a week of development time, and it wasn't going to be that much cost in terms of resources due to AWS. By the end of the week, they had a functioning prototype of what you see here, and by the end of the third week, they had a production-ready corporate video service for Amazon employees. We call the service Broadcast. As you can see from this screenshot, videos are made available to our internal employees. We post things up here from Q&A sessions with Jeff Bezos to talks by our principal engineers. And in fact, Broadcast has changed the way that we work internally as a company. We post everything up here, to brown bags, to training videos, and in fact, we use it in ways that the engineers that created it never even thought it would be used. For example, our warehouse workers use it to send pictures of what's happening in the warehouse to our engineers that are developing the software used in the warehouse. So it's really created an interesting collaborative environment across Amazon internal employees internationally. So how are the developers able to get this up and running so quickly? Here's the architecture of Broadcast. It's pretty straightforward. A web server fleet hosts the site, and employees upload videos to broadcast. They're then pushed to S3 encrypted, and Amazon Simple Workflow detects that there's a new video and pushes it to an EC2 encoding fleet. Once the video is encoded, it's pushed back to S3, and if there's no videos being encoded at that time, Simple Workflow shuts down the fleet of EC2 encoding machines. Once the video is encoded, it's then made available for employees to watch on broadcast. The developers were able to get this up and going so quickly because of AWS. AWS provided them the building blocks they needed so they didn't have to start from scratch from everything. For example, instead of building a workflow system, they were able to integrate with Simple Workflow. In addition, when they were in our Amazon retail data centers, just getting the boxes for an encoding fleet could have taken up to a couple months. Instead, they were able to get boxes within the order of minutes. That really allowed them to innovate very quickly and to try out new things. Another part of AWS that made broadcast successful is its ability to scale. Keep in mind, broadcast replaced something that no one was using. So they had no idea when they launched broadcast if it was going to be popular or not. And in the end, it turned out to be very popular very quickly. Instead of worrying about the success of their service launch, they simply added more EC2 machines and more S3 buckets. And in fact, the team has run broadcast for 3 years without having to worry about scaling. From the VP's perspective, because of AWS, he was able to take a risk on the developer's idea and get him a little bit of time to play around and see if it was going to work. In the end, it did work, but had it not, it would have just been a week of developer time and a little bit of AWS resources that he would have paid, instead of having something that would have lasted a long time. So using AWS has allowed our developers to try out more things more rapidly and to allow our business to take more chances on their ideas. While broadcast is a great example of how AWS can allow you to take more risks and enable developers to move faster, moving fast can have its downsides. Things can get messy if you don't maintain best practices as you move to AWS. The cloud is not a universal panacea. It can't cover up for messy engineering practices. An example of this is availability. Designing for failure is a fundamental design principle at Amazon. We design assuming everything can fail, and we can lose bits and pieces of our architectures and not impact our customers. This is core to our company culture in that we're constantly monitoring availability, latency, and error rates. In fact, we don't just look at failure from a hardware perspective, but we also feel that badly architected code is latent failures that are going to impact our customers later. And in fact, at Amazon, we prefer simple stateless services that talk to each other that compose our larger architecture. As we went to AWS, we maintained a culture of assuming everything will fail. We assume that hardware will fail, and in fact, we assume entire availability zones are going to fail. And one thing we learned when we moved to AWS is we didn't have to change our approach to availability. Instead, AWS provided us the tools that we needed to maintain a highly available system in the cloud. And in fact, because services were making some changes as they migrated to the cloud, we took advantage of this change to look at the lessons that we'd learned from availability in our own data centers and have the services architect as they went to the cloud to be higher availability than they were in our data centers. We have two different types of services at Amazon. We have customer impacting services, ones that if something goes wrong are going to negatively impact our customers, and non-customer impacting services. Ones that if something happens, it has no impact to our customers, but it might to our developers, such as our developer tool space. For our services that are customer impacting, we pay for high availability. And what that means you see here. When there's 3 availability zones, we retain our 15% buffer we talked about before, plus 33% extra capacity in case of an availability zone failure. We constantly monitor our availability zones to determine if something's happening. And if we detect something, we quickly flip out of that availability zone and enable the other 2 to handle the excess load, until at which point we determine the other availability zone is good to go, and we flip back to that. It's easier to do this type of architecture with stateless services, but we found that we can even retain higher availability stateful services with AWS. For example, with DynamoDB, AWS does our replication for us instead of us figuring out the right replication model. While I mentioned we have different types of services, AWS has also allowed us to have our non-customer impacting services be more highly available for our developers. For example, we retain logs for everything that's happening in the retail server space, just to analyze what trends are happening across the retail fleet. And developers are accessing this to do analysis. The team used to run a fleet of file servers, and if something was going wrong with one of those servers, they would shut down the ability to access the logs. This had no impact to our customers, but definitely made our developers annoyed when they wanted to get access to those logs and they weren't available. A couple years ago, that team migrated all of those logs to an encrypted S3 store. And as a result, we haven't had any of the availability issues we had because of S3 replication. In fact, new developers to Amazon can't imagine those logs not being available. So beyond good engineering, we've also learned it's important to have some governance as you migrate to the cloud. We want to unlock innovation, but we don't want to cause harm to our company or to our customers. One of the roles that the Move to AWS program has played in Amazon is determining when governance is required and how much governance is required at any point in time. An example of this is security, which is a traditional gatekeeper for a lot of enterprises. And you're going to be kind of branching out into new ground when you go to AWS in terms of security. So you can either treat your security team as an enemy in your migration or as a partner. We chose to engage our security team very early in the migration and to keep them appraised of what we were doing. And in turn, they helped us in architecting our solutions on AWS. As an example, when we started working on the Move to AWS program, every service went through a manual security review with a security engineer. At the rate that we were migrating to the cloud, this was not scalable at all. So we worked with our security team and determined AWS usage guidelines for different types of Amazon data. For example, public data that was available on our website versus customer-sensitive data. Security also created a straightforward way for all of our engineers to determine what level of data they had in their applications. As a result, the security team is able to focus their time working with the service owners of those with sensitive data and enabling those with non-sensitive data to move quickly to AWS. So what we've learned from enabling our developers to move quickly is that we can take more risks and say yes to more developer ideas. While this is great, you need to make sure that you pay attention to where governance is required. An example of that is to really talk to your security team as you approach your migration. Also, don't forget to retain best practices in your migration. The cloud can't cover up for sloppy engineering. You still need to think about availability and performance. Build your services, knowing your dependencies, build fault-tolerant systems, and learn about concepts like availability zones and redundancy models. Finally, here's the lessons we've learned so far as a company in our migration to AWS. You don't need to migrate all at once. Choose early migration targets carefully to make progress towards your migration and to create a cultural change that focuses your engineers on AWS service solutions. Also, enable your developers to move quickly and find ways to keep up with their speed of innovation as opposed to blocking their creativity. Lastly, you'll be surprised at the benefits you'll receive by going to AWS. I know that we have in Amazon Retail. I'll be available up front if you have any questions, and also if you have any questions about how your company can use some of the techniques we have. You can also find any of the AWS account managers or solutions architects that's here in the conference. They know about our use cases as well as many other companies that have done migrations and can help you work through what makes best sense for your company. In conclusion, we have had a great experience at Amazon Retail being an enterprise customer of AWS, and we expect and know that you will as well. Thank you.